One type of double-acting mechanism used on larger propellers, like the one shown here, achieves control of blade pitch angle by means of a hydraulically actuated piston connected to a cam slot, which rotates a bevel gear. The bevel gear engages with and drives other bevel gears located at the butt of each blade. Oil flow to either side of the piston is controlled by a propeller control unit. Alternatively, the type of control system shown here has a similar pitch change mechanism to the single-acting propeller. Like the single-acting propeller, its pitch change mechanism is also mounted towards the front of the hub, and the cylinder also contains a hydraulic piston. However, in the double-acting system, this piston will have hydraulic pressure directed to either side of it. Fine pitch oil is sent to one side of the piston, or coarse pitch oil is sent to the other. This eliminates the need for coarse pitch springs or gas pressure, and, with the exception of some larger propellers, the assistance of centrifugal counterweights. The double-acting propeller's controller will respond to the various demands made by the pilot regarding the propeller RPM to control the oil flow to either side of the piston in the pitch change cylinder in three ways. If the propeller is underspeeding, then the flyweights will be leaning inwards because of the reduced centrifugal force, allowing the speeder spring to push the landed valve downwards. This will allow the unit to supply oil to fine off the pitch of the propeller, while simultaneously porting coarse oil to return. The piston will move to fine off the blades, causing an RPM increase. If the RPM is as required, in other words the propeller is on speed, then a hydraulic lock is formed which traps oil both sides of the piston, maintaining the blade pitch constant. If the propeller is overspeeding, then the flyweights will be forced outwards by centrifugal force, compressing the speeder spring and allowing the landed valve to move upwards. This will simultaneously allow coarse oil to be ported to one side of the piston and fine oil to drain back into the engine from the other side. The piston will move to coarsen the blade pitch, causing a decrease in RPM. A constant speed propeller must be capable of all the pitch change operations mentioned previously, as they are selected by the pilot moving the RPM lever in the cockpit. The system must also be capable of maintaining a selected RPM within its own operational limits, regardless of changes in airspeed, altitude, and engine power setting. When the constant speed unit senses that the RPM is as has been selected, the system remains in a static state. However, any change in airspeed, altitude, or engine power setting will result in a tendency to either increase RPM above or decrease RPM below the value selected. As we've seen already, a tendency for RPM to increase, an overspeed condition, will be countered by a supply of oil being fed to the coarse pitch side of the piston in the pitch change mechanism. As is shown in this animation, the pitch will then coarsen and propeller torque will rise as a result of the increase in the blade angle of attack. Propeller torque now exceeds the engine torque and will cause the RPM to decrease back to the selected setting. As the RPM regains its previously selected value, the movement of the landed valve in the constant speed unit, which directed the oil flow in the first place, is progressively reversed until it regains the sensitive position, where a hydraulic lock holds the position in the pitch change mechanism immovable until the next RPM selection or disturbance in airspeed, altitude, or engine power setting. A tendency for the RPM to reduce, which is termed a propeller underspeed condition, must be countered by a supply of oil being fed to the fine pitch side of the piston in the pitch change mechanism. As is shown in this animation, the pitch will then fine off and propeller torque will fall as a result of the decrease in the blade angle of attack. Propeller torque is now less than the engine torque and will cause RPM to increase back to the selected setting. As RPM regains its previously selected value, the movement of the landed valve in the constant speed unit, which directed the oil flow in the first place, is progressively reversed until it regains the sensitive position, where a hydraulic lock holds the piston immovable until the next RPM selection or disturbance in airspeed, altitude, or engine power setting. Should an engine fail in flight, its propeller control unit would sense a drop in RPM, and, in an attempt to maintain the pilot's selected RPM level, would move to the underspeed or fine pitch position. Centrifugal moments acting on the blade would cause it to rotate towards fine pitch. This would result in the propeller being put into a windmilling situation, with its pitch change piston abutting the fine pitch stop. The immediate result of this would be a very large asymmetric drag, which would yaw the aircraft violently towards the failed engine. A second possibility, if the propeller continued to windmill and drive the engine, could be a complete mechanical breakdown of the engine, and even an engine fire. So, to minimize drag, and also to prevent further possible damage to the engine and the aircraft, some propellers, particularly on multi-engined aircraft, are provided with a means of turning the blades edge-on to the air flowing over them. In this edge-on position, where no aerodynamic force is generated either forwards or backwards, the propeller will cease to rotate. This action is called feathering the propeller. If the engine had actually failed, there would be no requirement to unfeather its propeller. However, propeller manufacturers usually provide an unfeathering facility, by means of which, if appropriate, an engine restart may be attempted. This may be a requirement following asymmetric flight practice. The operating principle of the propeller control unit incorporated in a feathering propeller is similar to that previously discussed, in that the unit contains an oil pump to boost oil pressure delivered from the engine or reduction gearbox, and a hydromechanical governor for RPM control. There is, however, the addition of a feathering mechanism, the operation of which will be discussed progressively throughout the lesson. Control units with feathering mechanisms may be found on both turboprop or reciprocating aero engines. Dependent on the manufacturer and type of propeller system, the controller may be known as a propeller governor, a constant speed unit, CSU, or a propeller control unit, PCU. For the remainder of this lesson, we'll refer to the unit as the propeller control unit, or PCU. The controls available to the pilot are, again, dependent on type. Most spark ignition piston engines, and many turboprop engines, are equipped with a twin-lever cockpit arrangement, whereby the pilot has separate engine power and propeller control levers. In this arrangement, propeller feathering can be manually achieved by moving the propeller control lever to the feather position, or on some aircraft, by means of a separate feather lever. Some turboprop engines utilize a single lever arrangement, whereby the pilot is provided with a power lever only. In this arrangement, propeller pitch, RPM, and engine fuel flow, power, are simultaneously adjusted. Feathering may be achieved by moving the engine high-pressure fuel cock to the feather position. New generation reciprocating engines equipped with full authority digital engine control, or FADEC, also use a single lever arrangement, whereby the pilot selects the required power setting and the propeller pitch angle is controlled either electronically by an electronic engine control unit or by a hydromechanical control unit. This diagram illustrates that the propeller control unit may contain a number of components which are additional to the basic constant speed system that we discussed earlier. The feathering mechanism provides a means of manually lifting the landed valve to the overspeed or coarse pitch condition when the appropriate control is moved to the feather position. The actions required to feather a propeller are dependent on the type of engine and propeller combination and the type of aircraft they are installed in. For single-acting propellers, this normally involves moving the propeller condition lever, or RPM lever, to the feather position. Moving the appropriate lever to the feather position mechanically lifts the landed valve against the speeder spring to its highest position, thereby simulating an exaggerated overspeed condition. The landed valve will remain in this position until the feathering control is moved back to its normal position. Any oil in the pitch change cylinder can now drain away, allowing the spring or gas pressure, assisted by counterweights, to move the piston onto the feathering stop. To unfeather the propeller, the speeder spring tension is released by moving the propeller control lever to a position comparable to that of the serviceable engine, which of course is running at normal operating RPM. This moves the landed valve down and connects the reserve oil pressure line to the fine pitch side of the propeller pitch change cylinder. A reserve of oil pressure may be supplied by means of an accumulator, which is charged continuously during normal operation. By activating a release valve, oil pressure from the accumulator is directed to move the pitch change piston to fine pitch. Alternatively, some systems may utilize an electrically operated unfeathering pump, or, on some smaller systems, the engine may require motoring over on the starter to build up sufficient oil pressure. Once the propeller blades have moved away from the feathered position, the propeller will start to windmill, and as long as the engine has fuel and ignition, it should start. When an engine, which is fitted with a single acting propeller, is shut down after flight, the propeller should be at the fully fine pitch position. There is a considerable quantity of oil trapped under pressure on the fine pitch side of the piston in the pitch change cylinder, which is holding the propeller in the fully fine position. This oil pressure is being opposed by the force of the feathering spring. After engine shutdown, the trapped pressure will gradually leak away past the landed valve in the constant speed unit. As this trapped hydraulic pressure leaks away, the feathering spring is able to slowly push the propeller blades towards the fully feathered position. While this condition would be acceptable to a turboprop with a free power turbine, it would result in an unacceptably high loading on the starter motor of a piston engine or direct coupled turboprop. So, to prevent the feathering spring pushing the blades all the way to the feathered position, on those engines where a feathered propeller would cause stress on startup, centrifugal latch pins are incorporated in the pitch change mechanism. The latch pins are held disengaged by centrifugal force while the engine is running. As the engine RPM reduces, small springs behind the latch pins overcome centrifugal force, and they are allowed into contact with the piston mechanism. Typically, the value of the RPM at which the latch pins become engaged is around 650 to 700. After engine shutdown, the latch pins engage with a groove in the piston mechanism, which locks the piston. This prevents it from being pushed beyond a predetermined blade angle, and further into the feathered position by the feathering spring. When the engine is started and RPM increases, centrifugal force will disengage the latch pins. Fine pitch oil will quickly build up and hold the propeller against the fine pitch stop. Note that if a propeller engine combination does have a centrifugal latch mechanism fitted, it may become impossible to feather the propeller of that engine once its RPM has fallen below the latch setting value. This is because once they are engaged, the latch pins can prevent the piston being moved any further by the feathering spring. It is thus extremely important to complete the feathering drill before the RPM decays below this figure.